All right. So I sent you a video dealing with this, the conversion of alcohols to alkyl halides, and we're just going to continue. We talked about on Wednesday different methods. We talked about the addition of HX, which works best for tertiary and secondary due to the carbocation intermediate. So let's go to the next method, which is here. I'm going to cut this so I can have more room to write notes. Another page. All right, so this is another method that works best for primaries. Let me put the date in. Man, it's almost February. That's crazy. All right, so we're going to look at this method today, and this is using PBr3 as a source of bromine. All right, and so again, this works with primary alcohols, and there are a couple of things about this particular reaction that we need to know. First of all, the stoichiometry of the reaction is 3 to 1. So you need 3 moles of alcohol for every 1 mole of PBr3. And the reason is all 3 of these bromines are going to get transferred, right, to an alcohol. Not the same alcohol, but that's why you need 3 alcohols to react with that. All right. So we're just going to go through the arrows because, again, we already know for all these mechanisms, they are very similar in the fact that the first thing you need to do is what? What are you trying to do to OH in each one of these processes?
Make it a better leaving group.
Make it a better leaving group. It's not going to leave by itself, but you're trying to substitute for it. So if you just added a bromine nucleophile, it's not going, the substitution is not going to happen on that hydroxyl, right? So you need something on the alcohol to make it a better leaving group. So you want to convert this into some leaving group Z, like I showed you in the generic example. So then the OH is now going to attack phosphorus and you'll lose a bromine. That bromine that you lose is eventually going to be your nucleophile. Or this is also a type of substitution. Right, so that bromine is eventually going to be your nucleophile. So when you lose it, it's over here just hanging out, waiting to attack, right? And I know I make this sound like the bromine has a mind and a brain and all that. I'm just trying to make it as plain as possible. So bromine is there, and now your hydroxyl group is now a much better leaving group than it was before, and it has a positive charge, so that makes it even more susceptible to be a leaving group, or more susceptible to departure. It's not going to happen stepwise though, right? It's not going to happen like if a leaving group leaving first and then bromine coming in. Somebody tell me why that won't happen this way with this example. So why wouldn't this step right here, the substitution part, because this is the, again, the rate determining step. Why will this not be stepwise?
Is it because there's no carbocation intermediate form?
Say that one more time. I can barely hear you.
I said, is it because there's no carbocation intermediate form?
Okay, that's part of it, yes. But look at the carbon where the carbocation would be, right? That's the point I'm trying to drive at. This is the carbon right here that if that leaving group left will become a carbocation. What's wrong with that? What type of carbon is that? Is it primary? Is it secondary? Is it tertiary? It's a primary carbon. And that's one of your worst carbocations, right? So, you know, the reason why it won't be stepwise is because that primary carbon is it's a really poor carbocation, right? So the primary carbon does not want to become a carbocation. I don't know if you all are noticing this, but there's a lot of overlap, you know, when we talk about certain things, like some topics just keep coming up. There's a reason for that. And the whole issue with carbocations and substitution, that's endemic to that topic, right? Unimolecular substitutions, or SN1, they proceed through a carbocation. Those that are, if it's stepwise and unimolecular, if it's concerted, then it's not going to proceed through a carbocation, right? It's just a direct substitution. What would the arrows look like here? How would I show the substitution? This is part one. We learned all of this in part one. How it doesn't matter which class you took either. What would the arrows look like for this reaction? This is nucleophile electrophile chemistry from part one. All right, well, how would I show that substitution?
The nucleophiles are gonna attack the electrophile.
Yes, which one of those would be my nucleophile?
Br, bromine.
Good. Right, and this goes all the way back to part one, probably week 4. That's my nucleophile. This is my electrophile, and it's the same arrows every single time. It does not change. If you mastered it, or at least partially mastered it in part one, this is not new. This is old, right? None of the stuff that we're doing is new. It's just a different application, but it's the same concepts. So you can see right here, I substituted the OH with a bromine, and then look where the OH is now. On phosphorus, right? So for this particular reaction, you first convert OH to a better leaving group, then it's a direct substitution. Let me move this, because I don't want to do this yet. Somewhere else. All right. So now let's go back and look at that. So in the beginning, I said that we needed 3 equivalents of alcohol for every 1 PBr3, right? Looking at the products, what can the PBr2OH do? What do you think? Can I take another alcohol and react it with that?
I think I saw in the video that you could.
Yeah, you can, right? That's why I said we need 3 moles of alcohol. So now I can take that, oh, I can take this right here. Let me move it over some. One second, let me get this together. Crop it. Right. So I can take that PBr2OH, which is a side product, and it's really not that I'm taking it, it's just going to happen again. So you running this in an Erlenmeyer flask or a round bottom flask. When you set the reaction up with that 3-to-1 ratio, this is going to happen 3 times. I mean, you don't have to go in and isolate PBr2OH and then add another alcohol to it. The stoichiometry is going to take care of itself. Right, so it's going to be this plus that. Do you think anything is going to change with respect to the arrows or the mechanism in that second reaction? Is something new going to happen? Something spectacular going to happen? Or is it going to go through the exact same mechanism?
The same mechanism.
Same mechanism. Nothing is going to change. The alcohol is still going to attack here, and you're going to kick off a bromine, right? You're going to get the same intermediate, well, similar intermediate, not necessarily the same intermediate. I just want to make sure I got the right number of carbons in here. Same thing, right? Now what's going to happen?
The nucleophile will attack the electrophile.
Same, just like in the previous step. This is going to attack this carbon right here, kick off that leaving group. All right, so now you're going to be left with, I think I added more carbons, but you get the picture. It's the process that we care about. All right. So now this is going to be here. I'll add another carbon up top if I have to. Plus P OH OH BR. I had to find my little glove again. All right. Nothing new, nothing different. Now look at what's left. Can that happen again? We said we needed 3 moles of alcohol to use up the PBr3. It has 3 bromines on it. So that means that I'm going to do that reaction. That reaction is going to happen 3 times.
Mm-hmm.
All right. So somebody tell me what the final, let me just copy this. Somebody tell me what the final reaction is going to look like. So it'd be this plus what? Is that right?
Yeah.
And without going, we saw the mechanism twice already. So without going through that, that final product is going to look like this. I'm just going to copy it. Plus what? What's the final version of the phosphorus going to look like?
It's just gonna have two OH groups on it.
Well, it already has two right here.
Without the
So it's going to have 3 OH groups. Is that right?
3, I'm sorry. Yeah.
Right. So this is the explanation for why you need 3 moles of alcohol, because you have 3 bromines on your bromine source, and all 3 are going to react with one of those alcohols, right? And it's the exact same mechanism every single time. Convert the OH into a better leaving group, and then you do a direct substitution of the intermediate. What type of substitution is that? We just said that there's no intermediate, there's no carbocation. So which class of substitution would that fall under? Would it be SN2 or SN1?
SN2.
It is a SN2 substitution. Right? It's a SN2. What if I ask you for that step to write the rate law? What would it look like? Anybody remember that from part 1? Go ahead. I hear somebody getting ready to chime in.
Are you talking about like the graph?
Not the energy diagram, the rate law, where we would say rate is the rate constant K times something and something or something. Right? If it's SN2, what does that 2 stand for? What does that 2 mean? Anybody remember that? It is bimolecular. So it's the K times the concentration of the nucleophile and, well, let me not say electrophile, I'll just say substrate. And the substrate. That's what the rate law looks like for SN2. So it's dependent on both the substrate, which is the intermediate with the oxygen phosphorus leaving group, and then the nucleophile is bromine. So both of those will have an effect on the rate. And then for the overall reaction, if we did the energy diagram, let me shrink some of this down first. What would it look like? How many steps are involved in this reaction?
It all happens at the same time, doesn't it?
Well, the first step is separate from the rate determining step though, right? See the first step where we make the intermediate? That's going to be separate. So that's a step. And then the substitution part is also a step. But remember when we talked about the substitution, we were saying that if that's the rate determining step, then that step is going to be slower than all of the other steps. So the whole thing is stepwise, but the rate determining step is concerted. All right, so the first step is quick. We'll say that this is quick and exothermic. And then the second step is going to be endothermic. So this is step 1, and this is your intermediate. And then this is the step 2, which is your substitution. Right, and then this is your product. And then these are your reactants. All right, so that overall reaction is stepwise, right? Because it happens in multiple steps. But the rate determining step, which is right here, is concerted. Meaning you go straight from whatever those reactants are to the product. And again, these are all approximations. We haven't calculated the activation energy. We haven't calculated delta H for each step, none of that, but it's just approximated. All right, any questions about any of this? Anything about this reaction? All right, let's look at let's look at this question right here. It's giving you the product. And it's asking for the start materials. What do you think? It's asking you to give the start materials. And look at my product. I have 3 bromines in the product. I have the phosphorus with 3 hydroxyl groups on it. What do you think that start material is? How would I get to this product using PBr3 as one of my start materials?
The alcohols would be the things getting replaced by the
Exactly.
bromine.
Go ahead. I didn't mean to cut you off.
Oh, I was just saying, so the alcohols would be the substituents.
Instead of bromine.
Yes.
Yeah. So here, this would be my start material. Right? Because again, all of these reactions where you converting an alcohol into an alkyl halide, they're all substitutions. So all I'm doing is substituting these OH groups with bromine, and I use PBr3 to do it. All right. Any questions about anything? All right, so this particular reaction again has a different extra added feature of looking at the stoichiometry, like the ratio between PBr3 and the alcohol. All right, so let's go to the last reaction, and then we're going to start working through some of these examples. The last reaction is here, and it is taking thionyl chloride, which is a different type of reagent. And I'm going to cut this because we need more room to work. So this is what thionyl chloride looks like. And it's used to convert mainly primary, but you can also use a secondary. All right, primary and secondary alcohols to alkyl halides. All right, and so with the thionyl chloride, it's also a mechanism or reaction that has multiple steps. But the outcome is the same. We are trying to take an alcohol and convert it into an alkyl halide. That's the goal, right? So this is thionyl chloride also with pyridine. right? Pyridine is this compound right here. It's a base. And we use it for proton transfer. All right, just like all bases, you put them in the presence of an acid. Now, alcohol is not a very good acid, but that proton is acidic, somewhere in the pKa in the range of 16 to 17. So it's acidic if you use the right base, right? So the purpose of that pyridine doing proton transfer is to make your hydroxyl group, or to make the oxygen a better nucleophile. Right, so once that oxygen is deprotonated, let me fix that. Once that oxygen is deprotonated, it's a better nucleophile. It's more reactive. If you remember from part 1, when we talked about nucleophiles and electrophiles, negative nucleophiles are always better nucleophiles than neutral nucleophiles. So sometimes if you're using a hydroxyl group and you want to make it more reactive, you just hit it with a base first to pluck that proton off. And you can see right here that it was pyridine that did the proton transfer. And you get what's called a pyridinium ion. All right. So now let's put the arrows in, because that's what we've been doing for all the rest of them, is doing the mechanism in addition to determining or predicting the product. So what would the arrow look like? And let me throw put a bond here. All right, what would that arrow look like to go from the OH to the oxyanion on the other side of the arrow? Like, how would you show that happening? So this is just a proton transfer reaction. What do the arrows look like for that?
With the pyridine base attack the oxygen, so like the arrow from the lone pair on the pyridine base would attack the oxygen.
Is it attacking? I'm with you. Is it attacking the oxygen or the proton?
I say attacking the oxygen.
All right, but this is it's a proton transfer, so it's actually going. Let me show you why it's not. If you remember from part 1, we talked about dipoles. So for the OH bond, the oxygen is partially negative and the hydrogen is partially positive. So anytime a nucleophile or a base is attacking, let's say the OH, it's not going to attack the oxygen because oxygen is already electron rich. It's going after the proton. And when that happens, the OH bond breaks, right? And those electrons go back to oxygen. So that's how you end up on the other side of the arrow with oxygen with 3 lone pairs and a negative charge. And then the pyridine has picked up that proton. You're right that the interaction is between pyridine and the OH group, but the electrons are actually going to attack the proton itself, because that's more electrophilic than the oxygen, if we think about it in terms of nucleophiles and electrophiles, even though it's an acid-base reaction. right? And it's due to that dipole between oxygen and hydrogen. All right, does that make sense?
Yeah, it does.
All right, so now we are done with the proton transfer. Now we look at the next step. Oxygen is now a better nucleophile. The pyridinium ion is not participating in this part. Now the oxygen is going to attack thionyl chloride. Right, look at the intermediate over here and tell me what happened. What did oxygen do to thionyl chloride? And where is it attacking? What new bond do you see in the intermediate?
It like took away the double bond between the oxygen.
Yeah, the double bond got broken. And do you also notice that there's now a bond between oxygen and sulfur? All right, so the oxygen had to attack sulfur and break the pi bond. Right, so you're attacking here like so. And then you break, let me put some electrons on this. You break the sulfur oxygen bond. Right, so that's how you end up with the intermediate here. So now this intermediate, again, all of these reactions are substitutions, and one of the main facets of each one of these reactions is making that oxygen a better leaving group. So now that oxygen is a better leaving group. So that's one other step where you actually, this sulfur intermediate undergoes an elimination. So this part is an addition. If you remember that from part one, right? Anytime you add or break a pi bond, that's an addition reaction, right? So it's an addition followed by an elimination, right? So you're going to kick off one of the chlorines, and that's just here, put the pi bond back and lose a chlorine. Let me put the electrons in here, right? So now this is, that should be negative, by the way. Right, so now you have, this is set up now. So now this is your leaving group. This is your nucleophile. It's set up now to do what type of substitution? SN2 or SN1? All right, so now it's ready for substitution. What do you think? SN2 or SN1, and why?
SN2.
Yeah, it's going to be a SN2 for sure. What is it about that substrate, whether sulfur leaving group is, that makes it more susceptible to SN2 substitution? Right? You can always tell by looking at the carbon where your leaving group is. If that carbon is primary, it's going to be SN2 without a doubt. All right, so this is a primary carbon. Right, so this is the substitution is going to be SN2. Anytime you have a primary carbon doing substitution, it's SN2, because that carbon the alternative is for the leaving group to leave first and leave that carbon as a carbocation, and that's not going to happen. All right, questions about that? The thionyl chloride reaction. And then you can see the product down here where the hydroxyl group got substituted with chlorine. And then what's left is, let me show you that, because the substitution part happens here where chlorine is going to come in and attack here and then kick off that leaving group. Right. So let me show you the side product. So this is the product, and then you get this O minus S double bond O Cl plus the pyridinium ion is still here. All right. And then these two will eventually do proton transfer between themselves. All right, so you end up back with pyridine plus that. Right, this is not going to stay this way because that pyridine is now able to go in and be a base again on another mole of alcohol, right, or another molecule of alcohol. Because even if you start with 1-to-1 ratio, 1 mole is Avogadro's number of molecules. So that pyridine can go in and start all over again, doing proton transfer with another alcohol and starting that cycle over again. All right, let's look at some examples down here. So it says, give the correct reagents to convert star materials, given star materials into the products, determine if it's SN2 or SN1, and draw a reaction energy diagram for A and C. Let's look at A. So let me give you your choices, right? So you can use, sorry about that. You can use HX, you can use thionyl chloride and pyridine, or PBr3. All right, so each one of these is going to be different. Each one is going to be different. So let's look at A. What do you think? If I want to convert that alcohol in A to that product, what would I use? What am I thinking about when it's time to turn an alcohol into an alkyl halide? What's the first thing I'm looking for?
And whether the alcohol is a good leaving group.
Okay, so we know the OH is terrible. So that's good. That's one thing. But what else am I looking for? I'm looking at the structure of the alcohol to see if it's primary, secondary, or tertiary, right? So primary and secondary alcohols, I'm going to use thionyl chloride or PBr3. Tertiary, I'm using HX, period. Right? That's the best reagent for tertiary alcohols. So what type of alcohol is A? Is it primary? Is it secondary? Is it tertiary? And how do I tell that?
It's primary.
So let's look at it. So here's the carbon where the alcohol is, right? How many carbons are bonded to that carbon?
Oh, well,
3. Right? So this is a tertiary alcohol. So I know once I identify the structure, then I can start thinking about what to use. All right. It's a tertiary alcohol. And so I need a reagent, a set of reagents that is that's going to facilitate converting a tertiary alcohol into a tertiary alkyl halide. So we know primary, secondary, we use either thionyl chloride or PBr3. For tertiary, we use HX. So what would X be in this case? If I'm trying to turn this OH group into bromine, what would X be?
Bromine.
Bromine. Good. It's HB. This so here, I would simply use HBr. Right. That's going to give me that particular alcohol. I'm sorry, that alkyl halide. Are y'all following that? Right. We again, there are three big
Yes.
topics that we're working with. Number one, we're working with synthesis of alkyl halides. We talked about allylic bromination, and that's one way. Now we're talking about another way to make alkyl halides, which is to take alcohols and turn them into alkyl halides. And then underneath that, we're talking about the different methods for doing that. So if you have a certain type of alcohol, you can only convert it with a certain type of reagent. If it's tertiary, you got to use HBr, HI, HCl, something like that. If it's primary or secondary, depending on what halogen you're trying to get, it's either going to be thionyl chloride or PBr3. I mean, there are other methods, but we're focusing in on these as the ones that we're learning for the scope of this class. All right, let's look at B. What type of alcohol am I working with?
Is it secondary?
It's a secondary, good. It's a secondary alcohol. All right, secondary alcohol. All right. Now, what is the halogen in the product that I've turned that alcohol into? It's a chlorine, right?
Chlorine, yeah.
So if I want to convert an alcohol into an alkyl halide and I want the halide to be chlorine, which one of these three reagents am I going to use?
Is it the thionyl chloride?
Thionyl chloride and pyridine.
Pyridine.
That's exactly right. So I'm doing God dang it, sorry about that. I almost cursed, but it's Friday. I try not to curse on Fridays. Thionyl chloride. I heard that. Don't be smacking. Thionyl chloride and pyridine. All right. Now, here's the thing. Let's go back and jog our memories, and then we'll be done because it is Friday. Look at what do you notice about the OH and the chlorine? What do you notice about that?
They're on the same carbon.
Yeah, they're on the same carbon. That's true. What else do you notice? Can you see that this one is on a wedge and in the product it's on a dash?
Are they
Even though it looks weird, can you see that? Right.
Yeah.
So in the product we have inverted stereochemistry. Right. Anytime you see inverted stereochemistry as a result of a substitution reaction, that is a 100% or 99.99% proof that the mechanism was SN2. That's one of the key characteristics of an SN2 mechanism is inverted stereochemistry. And we just went through the mechanism and we know that it's SN2 and concerted. We just showed that. So anytime you see that inversion like that, where you go from, let's see if we can figure it out right quick. This is, let me get a better pen. That's 1, that's 2 over here, and this is 3. Everybody agree with that prioritization?
Yes.
So that is clockwise, counterclockwise, is that right? And H is already pointed back. So we could just say that that's S. Yes, no?
Yes.
And this is 1, 2, that doesn't change. 3, that's counterclockwise. But what's the shortcut that we learned? If H is coming on a wedge, then what we see, we have to reverse it. Is that right?
Yes.
Yeah, so it's S on that side and it is R on this side. All right. So that inversion that you see is a consequence of that SN2 mechanism. Because when that chlorine nucleophile comes in and attacks, it's going to attack from the opposite side of where the leaving group is. Right. And now, if we had time, I would show you like how that would look. But we don't have time to do it. Maybe we can do it on Monday. But we're going to stop right here. All right. If you are, I'm going to post the test later this afternoon. So don't email me about it yet. It'll be posted sometime today. I got another class after this, and I got a break in between that and a 1 o'clock. So I'll try to get it done then because I'm still editing that exam, changing up some of the questions and things like that. So it'll be posted today. You'll have until Sunday to finish it at 11:59. There's no lockdown browser. There's no time limit. You can stop it and start it. All right. So all those questions are answered. Now, if you get kicked out of the exam or Blackboard glitches or something like that, by all means, email me or use that number I gave you to text me so I can reset your attempt. But everybody that's here is hearing it from the horse's mouth that the exam is open today and it closes Sunday. So if Sunday comes and there's no exam for you, then there's also no excuse because you heard it right here. Oh, I didn't know we had a test. We have a test today. It's going to be posted later and you'll have until Sunday to finish it. Are we all clear on that?
Yes,
Yeah.
sir.
All right.
Yes, sir.
Bet. Cool. So now go have a great weekend. Stay safe. Stay out of harm's way. And God willing, we'll come back on Monday. We're going to keep working on this until we finish it. And we're going to move to the next topic, which is organometallics, that's a real fun topic. Go ahead, Tia.
Can
Yes.
I talk to you after class?
We can talk
Yeah.
after my 10 o'clock. I got a class right after this. But I did
Okay.
see your email. So yeah,
Okay.
we can talk this afternoon. It's fine.
Okay. All right. Thank you.
All right. Anything else? All hearts and minds clear? All right.
I sent you an email too, Dr. Russell. This is Maya.
Did you see my message in the chat to you?
Oh, no, I didn't.
Come on, man.
I'll look.
Come on, man. Come on. I sent you a message like at the beginning of class.
Okay, I'll look now.
All right. Don't log out till you see it and read it. And feel free to reply back.
Okay, I saw it. Thank you.
All right. Have a good weekend.